So far, we've looked at four major topics in physics: kinematics, which describes motion, forces, which explain motion, and conservation of energy and momentum, which provide additional rules for motion. Now we are going to take all of those concepts and apply them in a new context: rotation. While the topic of rotation throws some new variables at us, virtually everything here is related to something that we have seen already. It's almost like a review of the entire course so far. Suppose you have an object like this turntable. We see 3 stickers on it. Let's switch on the turntable and allow it to rotate. We see the stickers start from an angle of about -45 degrees and end at an angle of 180 degrees. The positions of these stickers changed, and we can describe the change in terms of the angle they swept out. We can say they moved 225 degrees counterclockwise. This quantity, which describes the angle that the stickers moved through, is called angular displacement. Remember back in kinematics when we talked about displacement as change of position? Angular displacement is the change of angle. It tells you the angle through which an object rotated. Angular displacement is symbolized with the Greek letter delta theta. It is an angle, and it is expressed in a unit called radians. A radian is an angle measurement just like degrees. In fact, a radian is about 57 degrees. It is possible to convert a degree measurement to radians by using this formula. Multiply the number of degrees by pi and divide by 180. A rotation of a full circle, that's 360 degrees, is the same as 2 pi radians. 180 degrees is the same as pi radians. 90 degrees is the same as pi over 2 radians. 60 degrees is pi over 3 radians. 45 degrees is pi over 4 radians. 30 degrees is pi over 6 radians, and so forth. So the magnitude of the angular displacement is described in radians. What about direction? Well, there are 2 directions that something can rotate: counterclockwise and clockwise. Just as by convention we consider right to be positive and left to be negative, we have convention where counterclockwise is considered positive and clockwise is considered negative. So going back to our original example, if we say the turntable rotated 225 degrees counterclockwise, we can equivalently say its angular displacement was positive 5 pi over 4 radians. Now, how far did the stickers travel in terms of linear distance, that is, in terms of meters? While all the stickers traveled through the same angle, the one near the edge traveled a much greater distance than the one near the center. We can convert angular displacement into a linear distance using this equation down bottom. R stands for the distance from the center of the turntable to the sticker, and theta is angular displacement. Multiply these two together and you get the linear distance through which the sticker traveled. Note that for this calculation to work, the angle must be given in radians. This calculation does not work in degrees. So, if the innermost sticker was located 0.05 meters from the center, given that its angular displacement was 5 pi over 4 radians, it traveled a linear distance of 0.196 meters. And if the outermost sticker was located 0.2 meters from the center, given that its angular displacement was also 5 pi over 4 radians, it traveled a linear distance of 0.785 meters. Back in kinematics, we introduced another variable to describe motion: velocity, the rate of change of position, how fast something moves. As you probably guessed, in rotational dynamics, there is a quantity called angular velocity. It's the rate of change of angular position. Or, more simply, if regular velocity tells you how fast something moves, angular velocity tells you how fast something spins. Angular velocity is symbolized by the Greek letter omega. It is a vector. Colloquially, it is often measured in revolutions per minute, or RPM, how many complete cycles are made per minute. However, to stay consistent with angular displacement, we will use radians per second. If anyone ever gives you an angular velocity in RPM, you can convert it into radians per second using this calculation. RPM times 2 pi over 60 gives you radians per second. So, for instance, an object that rotates at a rate of 30 RPM has an angular velocity of 3.14 radians per second, or half a turn every second. Just like angular displacement, angular velocity is a vector. An object can rotate counterclockwise, which we symbolize as positive, or clockwise, which we symbolize as negative. These stickers take 1.3 seconds to complete one rotation. One rotation is 2 pi radians, so the angular velocity of these stickers is 4.83 radians per second. And since it's counterclockwise, the angular velocity is positive. Once again, we can also work out the linear velocities of the stickers using this equation. It's very similar to the earlier one for angular displacement. Take the angular velocity in radians per second, multiply it by the distance in meters, and you get the linear velocity. So for the innermost sticker, located 0.05 meters from the center, given that its angular velocity was 4.83 radians per second, the size of its linear velocity is 0.241 meters per second. And for the outermost sticker, located 0.2 meters from the center, the size of its linear velocity is 0.967 meters per second. And now we turn to angular acceleration. This is the rate at which the spin is speeding up or slowing down. It is symbolized by the Greek letter alpha and measured in radians per second squared. A positive angular acceleration means either an object is speeding up in the positive counterclockwise direction or slowing down in the negative clockwise direction. A negative acceleration means an object is slowing down counterclockwise or speeding up clockwise. And the size of the linear acceleration is once again easy to calculate. It is simply the distance from the center to the sticker multiplied by the angular acceleration. In kinematics, we interrelated the kinematic quantities using the toolbox equations, a set of handy algebraic equations that apply when acceleration is constant. Likewise, we can relate the quantities in rotational kinematics too. We get the equations at right. As you might notice, these equations look a lot like their linear counterparts. Let's try an example. Here we see a pulley wheel with a radius of 0.1 meters. Originally, the bucket is standing still, but it descends a distance of 15 meters in 8 seconds. What is the angular velocity and acceleration at the time that it strikes the surface of the water? We were given a linear displacement, an initial velocity, and a time. First, we need to convert these into angular terms. The linear distance that the bucket travels is equal to the linear distance traveled by the rim of the pulley wheel. We need to turn this into an angular quantity. Plugging in what we know, we get delta theta equals 150 radians. It's positive since the rotation is counterclockwise. Likewise, the initial velocity of the bucket can be related to the initial angular velocity of the pulley wheel. Since the bucket was standing still, the initial angular velocity of the pulley wheel is 0. We're looking for the final angular velocity, omega f. The only toolbox equation that relates the angular displacement, initial and final angular velocities, and time is the third one, which we have reproduced here. Plug everything in, and we get omega f is equal to 50 radians per second. Next, to solve for the angular acceleration of the wheel. Equation 2 will solve it for us. We get an angular acceleration of 8.33 radians per second squared. The linear acceleration of the rim of the wheel is equal to the linear acceleration of the bucket. Solving, we get a linear acceleration of 0.833 meters per second squared. This video introduced the variables of rotational kinematics. We introduced the concepts of angular displacement, angular velocity, and angular acceleration, and saw they were closely related to their linear counterparts. Even the toolbox equations are closely related to their linear counterparts. In the next videos, we will look into how to weave mass and force into rotational motion.